I have shared the YouTube link. I have shared the YouTube link.
Okay, but we'll inshallah start in at exactly I think 2:05.
Okay. बड़ा कहाँ से कितना है यहाँ से?
What?
हाँ नीचे बहुत से मेट्रो हाँ
सबसे नीचे से
ये व्यू में चल
व्यू में जाना था ना
चलिए और
सबसे नीचे Dr. Qammer, can you also make Saira Arshad a co-host? I tried, but I couldn't. Thank you.
No problem. Shall we start?
Just allow me one moment and then we'll start. Just one moment.
Sure.
Dr. Qammer, let's, I believe, start. So once again, I welcome Dr. Qammer Abbasi under this second training session being carried out by him under our British Council funded STEM Education in Pakistan project. For those who are joining us today who weren't there yesterday, I would again briefly introduce Professor Dr. Qammer Abbasi, who is a reader with James Watt School of Engineering, University of Glasgow, UK. He's also the Deputy Head for Communication, Sensing and Imaging Group, Program Director for Dual PhD degree, Deputy Team Lead for Quantum and Nanotechnology in the University's Advanced Research Center, Co-Manager for Ops and Terahertz Laboratory, and Lead for Healthcare and Internet of Things use cases with Scotland 5G Center Urban Testbed. He has a portfolio of more than 7 million and contributed to more than 350 plus leading international technical journal and peer-reviewed conference papers and 10 books. He has received several recognitions for his research, including URSI Young Scientist Award, UK Exceptional Talent Endorsement by Royal Academy of Engineering, National Talent Award by Pakistan, International Young Scientist Award by NSFC, and the list, I believe, goes on. And as I added yesterday, that I think one of the latest achievements or feather in his cap has been, 3 of their publications from his research being accepted into Nature. And I think earlier than that, another source of pride, I think, for Pakistan as well as Dr. Qammer was being awarded the best teacher recognition at University of Glasgow. So we're very honored and very glad to have you here with us for the second training session under British Council funded project STEM Education in Pakistan. So without, wasting any more time, over to you, Dr. Saab, please start.
Thank you. Thank you so much, Professor Akshay Shabir, for your introduction, a very kind introduction. And I'm so humbled to be part of this STEM education program funded through British Council. And I would like to thank British Council as well for providing me this opportunity. So I can see many of the names which were present yesterday. So like I said yesterday, the purpose of these talks trainings is to give you some future perspective, some vision, which can help you to flourish. And many of you will be researchers, some are already researchers. So the idea is to give in these talks some new ideas which you can go back and explore. And like I said yesterday, that many of the things you will see, they will not make sense in short term, but trust me, in long term, you will see all this. So today I'll be talking about healthcare mostly, and as the lead for healthcare use cases in Glasgow 5G testbed, my focus for today's talk is around how we can improve healthcare, which is a global challenge, and a development goal objective from UN as well, to provide a healthcare, affordable healthcare to all. So you will see in today's presentation, I'll start with something realistic, which you can see in short term, but later on you will be seeing something which I called Healthcare Vision 2050. So before going in detail, so some of you might have heard about body-centric wireless communication. This concept was coined back in 2000, and the idea was that how we can have sensors and system on or around the body to monitor or improve healthcare. The first question is, what is body-centric wireless communication or body-centric wireless networks? And it is mainly categorized as either on-body communication, when the transmitter and receiver both are on the surface of the body. For example, your smartwatch talking to your mobile phone, which is in the pocket. So both are on the surface of the body. The second type is off-body communication, when one of the node is on the surface of the body and second node is away from the body. For example, you are holding a mobile phone which is talking to a wireless access point, a Wi-Fi router which is away from your body. So that is called off-body communication. And the last one is in-body communication. In-body communication is when something is implanted inside your body and that implant is communicating to something which is outside the body. So that is called in-body communication. And body-centric wireless communication has a wide range of applications, starting from sports performance monitoring, healthcare, entertainment, and so on. But whatever technology comes, it has certain requirements. And the requirements for body-centric wireless communication are these systems need to be low power so that we have longer battery life. We all want that the devices we are using, they should have longer battery life, and we want them to be less complex, low cost. Of course, we want them low cost. And another threat nowadays is jamming issues and hacking issues. So we want a system which is robust to jamming and has low probability of detection. And of course, we also want system which can accommodate scalable data rates. For example, we want these systems where we can have transmission of low data rate signals and very high data rate. For example, you want to communicate videos as well. And of course, we want them to be very small in size. And each technology comes with challenges. If we want to fulfill these requirements, there are certain challenges at each and every level, starting from technology, where we want a new radio transceiver designs, novel antennas, which consumes less power, and the architecture. What we want is that it is user friendly, that anyone can use those systems, and they are context aware, that they can adapt themselves by looking at the surrounding environment. And we want software to be very friendly and easily adjustable. So this body-centric wireless communication is actually a multidisciplinary topic which demands for novel antennas, novel or new materials, bioengineering, and lastly, some intelligent networking. So this all comes under the umbrella of body-centric wireless communication. Now, what is the motivation for this research? And according to World Bank, the total number of elderly people who are 65 plus are 8% of total population, and that was in 2016. And this number has significantly increased. And according to US Bureau of Census, the number of elderly people is predicted to be 70 million in US by 2025 and around 16 million in the UK. And this rate is increasing significantly. And the ratio of elderly people is increasing very fast as well. And by 2030, this ratio will be around 24% for UK, 20% for US, and around 13% for China, which is very, very huge number. And what it's causing, so if elderly people are increasing, what will happen? So we are humans. So as we get older, our body deteriorates. So because of this increase in elderly population, there are more expenditure on healthcare for taking care in terms of medication, in terms of nurses, and so on and so forth. Now, this health expenditure is so much that it is projected that by 2060, for the UK, this health expenditure will reach to the 12% of total GDP, which is very, very huge number. And also, the per capita spending on health is increasing significantly as well, from 4 to 7%. Now, considering these challenges of increase in health expenditure, the current healthcare system model is in question, because if the cost is increasing so much, number of elderly people will increase. So what will happen? Of course, it will be difficult for governments to control this. So what is the solution? So we think that in future, we are going to have a system which is remote. So the patients or elderly people do not need to go to doctor. They will be monitored at home. And if they are being monitored at home, what this will do that it will save the cost in terms of traveling to doctors, in terms of saving the time for the nurse, in terms of, I would say, sometimes we go to the doctor, you have to wait for so long. At the end, doctor says, okay, you are perfectly fine. Just take paracetamol. But you look at the cost incurred from starting from home, reaching to doctor, this all has a cost circle. So what if we can monitor people at home by having remote sensory technologies, a multimodal sensory technology? So this can monitor people, and if we can detect something is happening to a person at home, the doctor can call the person and say, look, please come to see me. You are going to have some kind of anomaly in your heart in next 10 days. So these challenges can be resolved, and which will ultimately reduce the cost. So the idea is that we are going to have different kind of sensors at home, which includes point of care devices, which includes environmental sensors, which includes nanoscale sensors, which I'll talk later on. This all information will be gathered together and then will be transferred securely to the cloud, where some data analysis will be performed. And then that decision will be sent to doctor or carer, and then carer can look at that information and then can send intervention or feedback to the user. So there are so many commercial products available in the market in terms of wearable, which includes wristbands, smartwatches. And whereas for implantable, there are so many implantable products available in the market as well. One of my favorite one is this pill cam. So what it does is that you swallow this capsule which has camera in it. It's called wireless endoscopy. So you swallow that capsule, it passes through inside your body, take images and send it outside. Similarly, another one is this insulin pump, which is attached to your body with insulin filled in it. And what happens is that if your insulin level goes below certain threshold, this pump can inject the insulin. But if someone hacks this insulin pump, what will happen? Somebody can inject unnecessary insulin in your body, which can lead to death. So the point is, there are so many wearable, implantable products available in the market already. But the challenge with these technologies is that they needs to be continuously being worn by the user. They are invasive, like implantable products are invasive in nature. You need to do surgery for some of the products and then put the implant inside your body. And after 6 months, that needs to be replaced, or 1 year, which is not very friendly. And sometimes it causes infections as well. For wearable products, they need to be wear all the time. And then there are, we all have seen so many camera-based, vision-based technologies where cameras are being used to monitor people. But the issue is that with those technologies, privacy is being breached. So nobody wants to be monitored at home all time by cameras and data is being stored. So considering these challenges of wearable, implantable, and vision-based system, what we say is that we can make the healthcare system totally contactless. And that contactless is through ambient radio frequency signals around us. And those radio frequency signals are either mobile phone signals. Each home has Wi-Fi routers. So those Wi-Fi signals are radars. So the idea is that we can use those ambient signals around us to monitor people vitals, which includes heart rate and breathing rate. Because when you go to doctor, the first thing they look at is this. Excuse me. And then we can also use these signals to look at the gait analysis of the people, because the gait of a person is linked to various kind of disease. And for people who are living independently, sometimes they fell down and nobody knows. So for those elderly, independent living people who do not want them to be monitored by cameras, we can install this technology and it can be used to monitor them remotely about their fall. And over last 10 years in this contactless work, we have made significant progress, starting with monitoring of single subject activities, then moving to single subject vitals monitoring. Then a couple of years ago, we went to more realistic scenario, which is multi-subject monitoring. That what happens is that if you go to any care home, if you go to hospital, there are multiple people, and usually in one home, there are multiple people living. So we need to monitor multiple people, which is more challenging. And then we looked at multi-subject vitals monitoring as well, which is, we have filed patent for it. It is even further challenging, complex environment. And then we use this technology to look at some of very futuristic use cases. For example, looking at emotions of someone by using these wireless signals without any cameras or sensors, try to read sign language, which in our case was British Sign Language. And we also use these signals to read the lip movement to understand what someone is saying without using camera. So in next few slides, I'll quickly give you some of the glimpses of the results we did in this domain. And of course, anyone can contact me by my email, which I'll show at the end of the slide. If you want more details, everything is published and you can find online as well. So we started with a single subject activity monitoring. As I mentioned earlier, that we looked at various activities, which includes exercise, sitting, standing, walking, bending. And then we used our contactless sensing system, where what we do is that we have a transmitter, we have a receiver. We look at change in amplitude for channel state information. Then we apply machine learning and deep learning to classify those activities. And in this case, our accuracy was 90% to monitor the activity of a single subject. Then we looked at measuring the breathing rate of a single subject. So we asked the subject to perform different kind of scenarios, which includes normal breathing, shallow breathing, and elevated breathing. And then we used an off-the-shelf respiratory belt, which is Vernier Go belt, as a reference. So we asked the subject to wear the belt, which we bought off the shelf, which is being used to measure breathing rate. And then we used our contactless sensing technique to see if we are getting correlation between the two results. And our detection accuracy for breathing abnormality was 91%, and there was a very high accuracy. So we try to measure this activity and breathing in real time as well. So what I have shown in previous slide, it was we collect the data, we process it offline, and then we show the results. But in reality, we want this system to work in real time. So here is a real time demonstration for single subject activities. And you have seen that we can detect activities in real time contactlessly what someone is doing. And then we move to more realistic scenario, which was looking at the activities for multiple people. And here we used 5G frequency. So we published this paper in Nature, and the experimental scenario was that we asked 4 volunteer participants, and of course, whatever work I'm presenting, we took ethical approvals to study that. So transmitter was placed at one end, which is actually a Wi-Fi router. Then there was one receiver antenna, which was receiving the signal, and subjects were performing activities in this room. And we were using 5G frequencies, which is 3.75 gigahertz. And then we applied a deep learning on the data, and we found out that our system was capable of identifying with 95% accuracy if room was occupied or not, and then with above 90% accuracy, different activity classification. So we collected around 1,700 samples for 16 different classifications, and we were able to demonstrate an accuracy of up to 90% for 4 subjects, that what kind of activities they are performing in a room. Now, this work was very interesting. We were being approached by many partners that they want to measure people heart rate and breathing rate from 1 to 2 meter distance. So what we did, that we tried to measure the heart rate and breathing rate for multiple subjects, because what if in a classroom there are multiple students sitting and you want to see their heart rate or breathing rate. And also when we go to emergency, there are so many patients waiting in an emergency room. What if we have this system installed there and their heart rate and breathing rate is being continuously monitored? And if there is some anomaly anywhere, that patient can be brought forward from the queue to be seen by the doctor. So what we did was that, again, we use same technique to measure heart rate and breathing rate for 3 subjects. But here we used a baseline polar belt for heart rate, which we bought off the shelf, and then go vernier belt for breathing rate. And we were able to demonstrate with above 95% accuracy that we can measure for multiple subjects the breathing and heart rate. And I think this demo video will explain in a better way what I am saying. Hello everyone, Qammer Abbasi. Today we will show you a real-time video demonstration for multi-subject vital monitoring. This includes breathing rate and heart rate by using a contactless solution which we have developed in our group. We are using the polar belt as a reference for heart rate monitoring, and we are using vernier respiration belt as a reference for breathing rate measurement. What we are trying to do here is that we are using ambient radio frequency signals around us to measure the vital contactlessly. So on my left-hand side, we have a transmitter antenna, and on my right-hand side, we have 2 receiver antennas connected to a software-defined radio. And in the middle of this transmitter and receiver, we have 3 subjects wearing the reference belts. And these are our PhD students. And we are receiving the signal at receiver side. And then we do post-processing to extract heart rate and breathing rate out of it. So as soon as we will turn on the system, so we have a real-time display of heart rate and breathing rate. On the left-hand side of the screen, you can see that in the black, we have the reference heart rate coming from polar sensor, and in red is the results which are coming from our contactless solution. On the right hand side of the screen, you can see we have a breathing rate in real time by using the reference bed and also the contactless solution. And these readings are updated every 10 seconds, as you can see on the screen. And this solution is scalable to more than 3 subjects and less than 3 subjects as well. So you have seen that we can measure heart rate and breathing rate for multiple people in a realistic scenario. So as I mentioned earlier that we look at some of the more futuristic use cases as well. So one of the challenge with current hearing aid devices is that the user get a cocktail effect, which is a surrounding noise, and they do not like to wear the hearing aid device because of this issue. So our idea is to make that hearing aid device autonomous and self-adaptable, that it learns from the surrounding environment and suppresses the cocktail effect so that the user get a high quality of service. Now, if you want to have that kind of autonomous self-learned device, we need to give various kind of input to that device in addition to audio only. So the idea is that if you can add to that device some other dimensions, which includes, in addition to audio, you include the lip reading from another person. But if we use camera technology to do it, people don't like it because it invades their privacy. And also same is for the sign language as well. So what we did in this work was that we used both radars and of course our Wi-Fi based solution, which is we use software defined radios to monitor people lip movement. In our study, what we did, we used 1 male and 2 female participants for 2 different environments and collected around 1800 samples. One interesting thing, in COVID, someone asked us that, oh, what if someone is wearing a mask? How we'll see with the camera technology that what some person is saying by looking at their lip movement. But with camera technology, we cannot do that. But surprisingly, with this contactless sensing solution, we can monitor people lip movement under the mask as well. And we published this in Nature. So what we did was that we did the data collection for lip movement with and without mask by using both radar and Wi-Fi technology, and our detection accuracy was more than 85%, which was amazing considering we do not have to use camera technology. And then similar was the case for British Sign Language. We looked at 16 different expressions which are being mimicked in the lab, and we collected more than 300 samples and tried to classify or differentiate between different expressions, and our detection accuracy was 93.3%, which was amazing in this case by using VGG 16. Now, up to here, I was presenting this macro scale healthcare system by using ambient radio frequency signal around us. And that was basically to overcome the disadvantages of camera, wearable, and implantable technology. Now, there is another solution to implantable technology issues, that you make sensors which are so small in size that they are accepted by your body. So with the evolution of nanotechnology, which helps to reduce the sizes of devices comparable to cells and molecules, have attracted the attention to use nanotechnology in body-centric wireless communication domain as well, because of the materials like graphene and nanotube, we can reduce the size of the device to such a small level that they are accepted by the body. So the idea is that in future, I'm going to have a one capsule which has 100,000 of nanosensors in it. I swallow that capsule. What will happen? Inside that capsule, there will be nanosensors which will be dispersed all around my body, inside my body, and they will measure either cell temperature, chemical changes, and then by using that data, we can proactively detect if some kind of anomaly going to happen in that person. So the idea is, as I mentioned, our big idea is to make the healthcare system proactive. Proactive means detecting before something happens. So there's no nano sensor yet out in the market, but this is an envisioned nano sensor, which will be going to have a nano power unit, a nano processor, of course, transceiver, a nano sensor for sensing, a nano antenna, which makes it wireless. That if I have nano sensors which are inside my body, they collect this information, they need to transmit it outside my body. So we want that to happen wirelessly. So for that, we need nano antenna as well. And these nano devices will be very small in size, so they will have a limited capabilities. So the idea is that we are going to have a network of nano sensors to do certain kind of action. And the overall architecture for the system will look like, which we proposed back in 2017, that there will be nano machines. For example, in this case, inside my body, they will be measuring various kind of parameters, as I mentioned earlier. As these devices are limited in capabilities, they will send the data to a nano router, which will have a much higher capabilities than nano sensor. And then that aggregated data by nano router will be sent to the network, whatever will be available at that time, maybe 7G or 8G or 9G. And then data will be processed on a system which can be cloud, laptop, mobile phone, and then it will be sent back in a same route to do some kind of actuation. For example, if I want to do a targeted drug delivery, that can be done this way as well. And these networks, nano networks, connectivity with the traditional network defines a new paradigm, which is called Internet of Nano Things. I'm sure many of you have heard Internet of Things, but the idea is that in future we are going to have Internet of Nano Things, where we have a nano network connected to traditional network. And their applications are immense. I was just talking about healthcare, human health, but these nanosensors can be used for chip-to-chip communication, for monitoring plant health, like I was mentioning yesterday as well, that these nanosensors can help us to look at the molecular changes inside the plant to help us to do proactive detection. Now, the question is, as I said, that a nano sensor is a very small device with limited capabilities, and we need to have a network of these devices to make collective decision. So now the question is how these nano sensors will be talking to each other, and how we will bring, in case of in-body communication, how we'll bring that information out, what kind of paradigm we will be using for this. So there are two paradigms. The biomedical scientist says that those nanosensors will be talking to each other via molecular communication. But we electromagnetic scientists, we say that they will be talking to each other through electromagnetic communication. And the size of nanosensor is comparable to the wavelength of terahertz frequencies, which are much, much higher frequencies. So we believe that because the wavelength of terahertz is comparable to the size of nanosensors, hence we can use terahertz waves for communication and connectivity between these nanosensors. And terahertz has various advantages as well. So terahertz band is highly selective. As you can see that a band from 0.1 terahertz or 100 gigahertz up to 10 terahertz is considered as a terahertz band, and it is the band between infrared and microwave. And this band is highly frequency selective, and it imposes non-ionization hazard. So there is no ionization hazard to human body or to biological tissues. And these features make terahertz band an attractive band for the connectivity and communication of nanosensors. Now, before developing these systems, you need to have a link budget calculation, that what are the requirements for these systems, what will be power requirement, modulation, distance, gains, so on and so forth. So for that, what we did that we try to do those kind of experiments in the lab to see if we have this kind of nanosensor in the body, so what kind of losses we will get. So as we are trying to work at terahertz frequencies, the skin depth is very small. So we thought that in this case, we do not need to look at all human tissue. So if I want to have a nanosensors under my skin, so that's all terahertz wave can penetrate into. So we do not need to look at fat and other tissues. So what we did that we try to look at the channel models for the skin tissue. So before going in detail of that, we need to know that skin has three layers, which is epidermis, dermis, and subcutaneous layer. And the thickest among is dermis layer, which has different fibroblast cells and collagen. Now, we basically, what we were trying to do that we took those skin samples, we bring them to lab, and we try to perform terahertz time domain spectroscopy to see what kind of losses we are getting. The idea was that when we will be having a nanosensors, we need to know that how much transmission distance we can get. So one interesting thing, we found out that we were working closely with Bizard Institute in Queen Mary University of London. So we bring real human skin samples, we bring them to lab to do experiment. But the challenge was that in this transportation, the water evaporates from the tissues, and terahertz is very sensitive to water contents for its sensing capabilities. So because of that reason, we were not getting good results. So what we did that we have artificially cultured skin in our lab, and this is the artificially cultured skin in our lab, which was being developed through certain recipes where we take fibroblast cells, we seed them, then we put them with the collagen reagent, then we put some gels, and then we incubate it to have this artificial skin, which you can see here. And of course, we use cell culture hood to develop that skin. So I'm skipping it. So one thing, what we were doing is that we have developed various models of skin or samples of artificial skin. And as we were basically using different fibroblast cells to make skin sample or a artificial skin sample. So what we did that we used different densities or cell numbers. For example, we used in one of the artificial skin 100,000 fibroblast cell, in the second 300,000, 500,000, to see how terahertz wave will be impacted by change in the cell number. So we performed an experiment by using terahertz time domain spectroscopy. So the working band was from 0.5 to 2 terahertz. We did transmission based measurement for both real skin and artificial skin. So this was a sample holder where we placed our artificial and real skin. And once we place in sample holder, then we use this system, which is called terahertz time domain spectroscopy. So what it does is that we have a laser source, which we down convert to generate a terahertz pulses. And then we place a sample holder here with sample in it. The terahertz signal passes through it. We receive at other side. And then we try to look at the absorption in that system. So we did a reference-based measurement. What does it mean? We use this sample holder. We did a measurement. Then we place this sample inside sample holder. We did another measurement. So if we just simply subtract this reference measurement, then we will get losses or absorption inside the sample. So this was a real terahertz system which we were using in Queen Mary University of London, different electronics, different mirrors to have terahertz aligned. And then this was the sample holder for our sample measurement. And this is the microscopic image of the terahertz, not the terahertz, sorry, the skin sample where you can see epidermis, dermis layer, and some sweat ducts as well. And this is what we got from our system. So we did a measurement where there was no sample holder, it was only air. So this was the received signal at detector site. Then we placed the sample holder. There was no sample which was basically skin tissue inside it. We got this green signal. And when we placed the sample, we got this red signal. So you can see clearly delay, of course, and change in amplitude of the signal as well, which tell us the absorption. And this was for an artificial skin, the reference signal and the collision signal. This was the frequency domain characteristics, and you can see a very high dynamic range for the artificial skin. And if you remember, I told you that we use different fibroblast cell number to develop our artificial skin. So if you can see, we have used 100,000 to 500,000 fibroblast cells, different samples. And when we have passed terahertz waves through them, there was a clear distinction. And the reason was that when there were more cells, what happens was that we had the same sample size, and in smaller sample size, we had more cells. So what it was doing that when there were more cells in same sample, the cells were very close to each other. So when terahertz wave was passing through those cells, it was getting more hindrance. Whereas when there were 100K cells, there was some kind of spacing between the cells, so wave can propagate easily. So we found out that we need to look at the cell number in a sample which is directly linked to the absorption of terahertz wave. So we tried to get the refractive index and we did polynomial fitting, and the value was between 2 to 2.5 for a real skin. Whereas for different cell densities, as I mentioned, we tried to look at refractive index as well. And then interesting thing we did was that we use our system to characterize the artificial skin and melanoma. So we were working with Madix. So what we did, we had an artificial skin and we injected some of the cancerous cell in it, which helped us to read what is happening. And the results showed that the melanoma sample, which were basically where we injected some of the cancerous cells, have higher refractive index and absorption coefficient than artificial skin. And the reason was that melanoma samples have higher water content than artificial skin. And the main reason for melanoma containing more water is that the tumor cells degrade the contraction of the collagen lattice. And in addition, we looked at the refractive index and permittivity of melanoma sample, which was larger in variation as compared to normal skin. For example, the refractive index of normal skin at 0.5 terahertz increases 4.3%, while that of melanoma sample, it increases by 8.7% when the cell density rises from 0.1 to 1 million per milliliter. So our results clearly shows that we can differentiate by using these futuristic nanosensors working at terahertz wave to differentiate contactlessly melanoma and normal skin. So the main takeaways were that, of course, this is our just 10 years work. So we need more studies to understand these phenomena. And we need to look at phantom research more and more. And our future work involves how we can add more proteins to collagen and compare it with real skin, and also looking at the polarization effect of this system to see how polarization impact the properties of a tissue when a terahertz wave is being passed through it. And this was our breakthrough result, which we presented for the first time, channel model for in vivo communication. So this is our mathematical model, which we proposed, the red one, which was a parameter of distance, frequency, and number of sweat duct, and these black were the measured one. And the standard deviation was around 6.23 dB and mean error was 2.1 dB. And you can see there was some uncorrelation in this range, which we still don't know, and we are trying to investigate. So I'll take 5 more minutes. I know I'm running over time. So what other thing we did was that these measurements are very expensive. The terahertz time domain spectroscopy costs more than 700,000 pounds, and it is very difficult to repeat measurement. So the ultimate solution we engineer do is to do a numerical modeling. So the idea is that we can use on our computer, develop models which can mimic the real scenario. So what we did was that we try to mimic the real skin in modeling, and it took a lot of time for us to understand it. So this was the optical tomography image of human skin. This was a stratified model we come up with. But how we started was very interesting, that we started with a simple homogeneous skin model because we had the measurement results. So we went back, we compared the results. They were not making sense. Then we found out that okay, let's make it inhomogeneous. So this was dermis layer, this was epidermis layer, dermis layer. We made it inhomogeneous. But the interface between dermis and epidermis was considered flat, as you can see. But when we looked at this optical tomography image, you can see that between dermis and epidermis, the interface was not flat. And there was something here as well, which is called actually sweat duct. So we try to model the interface between dermis and epidermis as a non-flat surface. We try to look at results, still they were not very close to measurement. Then we found out that we need to model sweat ducts as well. So we modeled sweat ducts, results get improved. Then our future work involves adding capillaries and many other complex scenarios. So the conclusion for this simulation and measurement result work was that path loss depends on number of sweat ducts and follows linear relationship with distance. The roughness of interface has a great effect on wave performance, but still there is so much work needs to be done. So we are still trying to investigate this work. So with this, I'll just say thank you to all for listening to me. And I know in this talk, instead of giving you many answers, it was more open questions for all of you to work on. And I would sincerely like to thank all my colleagues, students, and funders for supporting this research. So thank you. So I'm open to any questions.
Sir, I have a question, and that is this system available commercially or just research is going on?
So I said initially that this system is not commercially available yet. I call it Healthcare 2050. So it will take some time. It's still in research phase. Yeah.
And sir, what do you think that I think it's really expensive as compared to if we go to the doctor and just give a checkup for all the details, healthcare details. So I think it's expensive.
The system will be expensive, you mean to say?
Yeah.
No, so whenever, let me give you a very simple example. So if we go 5 to 10 years back, smartphones were so expensive, nobody was able to afford it. And now if you go out in the market, there are so many suppliers and you can get a smartphone even in 5,000 PK rupees. So
Yes.
the idea is that when some technology comes initially, it is expensive, but over the time, it gets affordable because everyone has a mobile phone, everyone has a television. So if you look back in 1990s, I don't think so everyone had a phone. It was only very, very rich people can afford that. So within 20 years, everyone has not one phone, multiple phones. So same is for this technology as well, that over the period of time, it will be part of our daily life.
Yes, sir. Thank you.
Assalamu alaikum. I'm Dr. Huma Tasif. First of all, I would like to thank you for sharing these very innovative work of yours with us. I have multiple questions. One of the question you have answered already, because I had the cost comparison in my mind as well. My other question is, are these data sets available for research for public or not?
Yes, so the contactless sensing data set is all available on my website, web page actually. So anyone can use that data. There is README file as well, which clearly explain the data. So open data set is available. Yeah, if you couldn't find it, just drop me an email.
Okay. My other question is that what was the need to develop the artificial skin cells that you developed for your research? Couldn't you work on real skin cells?
Yes, that's very good question indeed. So we started working with real skin tissues, but the challenge was that when we tried to bring them from the hospital to the lab, in the way the water evaporates, so the moisture evaporates. So terahertz, for example, as I have shown one of the results for melanoma and normal skin, the real indicator to show difference between the normal skin and melanoma was water contents. So if we were using real skin, because of the time frame until we bring it to the lab, most of the moisture contents evaporate. So terahertz cannot detect clearly what was there. So hence we develop artificial skin so that we can control the environment so that moisture do not evaporate and we can measure it.
Thank you so much for clearing and a very useful talk for us. Thank you.
Thank you so much.
Excuse me, sir, I have a question. Sir, as you told, nanosensor are used to detect the presence of molecule, species, even single molecule atom. But I think they are having a possible threats to security and privacy of and health of human beings.
Yes, that's indeed a very good question, the security and privacy. So we work on security and privacy as well. Not only so the one of the work I presented initially, the contactless sensing work. So the idea of presenting that work was that we are not using cameras, so it is not invading your privacy. For nanosensors, if you remember, I gave one of the example for insulin pump, that if somebody hacks it, anyone intruder can inject extra insulin in your body, which can lead to a serious condition. So for nanosensors, of course, it will be a similar issue. So we have proposed because of time limitation, I didn't present that work. We have proposed in one of our paper that we can use path loss as an indicator or a fingerprint to differentiate between Alice and Bob, between legitimate and non-legitimate user. So we have demonstrated that, and there are some papers we have published, which probably you can look at.
Thank you, sir.
Any other question? If there is no question, I would like to thank you all for listening to me and have a really nice coming weekend. Thank you. Bye-bye.